Professor Mохд Rizal Arshad. You can start your presentation.
Okay, can I start now? Yeah. Okay. Okay. Very good evening. Thank you very much for inviting me to present for online sharing on the topic of bio-inspired approaches for developing robust autonomous robotic platform. So my name is Mохд Rizal Arshad, or you can call me Rizal. I'm a full-time academics faculty member in Universiti Sains Malaysia, USM, in one of the major public university in Malaysia. So USM was established back in 1969, and it is one of what we call the apex university in Malaysia. So the objective of the talk are 3 points. The 3 purposes of the sharing. First, I hope you can see the slide changing for the second page. First is to present some elements of bio-inspired approaches in developing autonomous robotic technologies. And then also I would like to discuss some design parameters for the design of such bio-inspired robotics platform. But in my talk, I will focus more towards marine robotics application. Since my research group, we have been focusing on autonomous marine robotics for the last, I would say, 20 years, since the year 2000. And so I would like to share some of our findings and also observation from the research work that we have done. And also, finally, is to discuss some potential way forward for bio-inspired autonomous robotics technology. So I just would like to show, this is not my system that we have, it's not mine. This is what the National Oceanographic Center, the NOC, Autonomous Vehicle Fleet in the United Kingdom, what they have in Southampton on the southern side of the UK. So you can see here the fleet of autonomous marine robotics platform, which have been used extensively to explore the oceans around the world. And then they can go quite deep, very deep. We know that the average depth of the oceans is around, of the world is around 3,800 meters, which is about 3.8 kilometers. That is the average depth of the oceans. And we have the deepest point, the Mariana Trench, is around 11,000 meters. And we have, for example, the Indian Oceans is about, on average, around 5,000 meters or 5 kilometer average depth. So that so you can see that the 71% of the Earth's surface are covered by water. So that's why the design and development of marine robotics, autonomous marine robotics, are very exciting and very critical for the world. So of course, in terms of the principle of the design of autonomous robotics platform are quite similar when we're talking about in terms of fundamental of it, in terms of whether we're talking about marine robotics, aerial robotics, terrestrial or mobile land-based robots, mobile robots, autonomous platforms. The principle, the fundamentals are very similar. It's just when we talk about the applications of the robots in the environment where we want to deploy the mobile robots, then that's where the fine-tuning or the design of the robot will have to be tuned towards that particular applications. Of course, here we have in my research group, we are focusing on autonomous robotics platform for marine application. So we have been developing this. Of course, we have also developed land-based mobile robot, terrestrial mobile robots, autonomous mobile robots for inspection application, etc. But this is our main focus. For the underwater robotics platform, we're talking about autonomous robotic platform for marine application. There are many applications. I just want to highlight that For autonomous robotic platforms, the application are tremendous. Be it for marine application, for land, forest mapping application, forest monitoring application, for example, there are many applications. So when we talk about specifically about marine robotics or underwater robotics platform, they are, for example, for seafloor mapping, for rapid response to oceanographic and geothermal events, for geological sampling. For example, for environmental application, you're talking about long-term monitoring of hydrocarbon spills, radiation leakage, pollution, environmental remediations, for example, inspection of underwater structures, including pipeline, dams, etc. So there are many applications for autonomous robotic platform. And this is just for the marine applications. So you can see that there are high demand for robust system which can solve the specific needs of the application accurately, efficiently. At the same time, it also versatile enough to be retuned for other kind of different kind of applications. Of course, here we have science, scientific, environmental, military application. Of course, the developed nations of the world are focusing a lot of resources on military applications using autonomous robotic platform for military applications. Then you have, of course, we have the ocean mining and oil industry, for example, ocean surveys, resource assessment, seismic mapping, etc. And of course, other applications related to the marine environment. For this, I'm giving an example for the marine application. But as I said earlier, it is the fundamental of the design are very similar. It's just when you look at the environment, each environment poses different constraints, different problems for the design of the robotics platform. For in this particular section on other application, you have the ship hull inspection, ship tank internal inspection, nuclear power plant inspection. All these needs the use of autonomous robotic platform in order to reduce the risk of human being having to execute all these very dangerous and risky tasks. So in terms of evolution of marine robotics, as I said, my talk, I will use the marine robotics as an example of why later we need to talk about bio-inspired design. For marine robotics, it started back in, I would say, back in the early 1900s, when we where people start in the 1950s, in the 1920s, 30s, when 40s, sorry, when they start to design many ocean-going, underwater ocean-going kind of craft. So you talk about purely supervisory design where it has less autonomy, very direct supervisory control by a human being. Then you start to talk about unmanned system where you have semi and full autonomy of the robotic platform. And this is where basically where you have autonomous robotic platform fit in, where this is where you have the autonomous autonomous robotic platform as an unmanned or fully autonomous craft. Then we have what we call the hybrids. Now people have been exploring on the hybrids, which is the where it can switch between supervisory and full autonomy. So around this evolution of autonomous robotic platform design for marine application, it goes the same evolution are happening for land application, the same are happening for aerial application, even for space application. These are mobile robots, for example, which countries like the US and the China, they've sent to, for example, to the moon, for example, and even to Mars, for example, mobile robotic platforms. Fundamentally, the designs are very similar. It's just when you talk about specific environment, that will determine the constraint and the limitation of the design. So more on this, so you have, for example, the issues of autonomous navigation, long-term deployment. For example, one of the major issue when we design autonomous robotic platform is the issue of power usage. How long can you deploy it before it runs out of power? So you talk about recharging, you talk about using the solar energy, using, for example, wave energy, using a number of other items, methods in order to recharge, to ensure that the power storage are sufficient for that particular application or for long-term deployment. And that's one approach. The other approach is to ensure that the utilization of power are optimized for that particular robot mission or deployment. So you have, of course, you have swarm intelligence, the use of swarm intelligence, the use of AI in decision making, in classification, in doing decision making. Okay, then you talk about smart power generation and management. You talk about robust sensor modules, and the more sensors that you have on the robot, the more power usage that it needs, and also the needs, and also how you integrate all the data in order to make decisions. So these are issues that one have to face and one have to solve in order to design very good, robust, effective, or workable autonomous robotic solutions. So, of course, in terms of compared to us, the robots that we design, there's so many angles that we have to learn from nature, because from biology, there's so many solutions that are there out in nature that we can use, that we can get inspiration from in order to solve our limitations. You talk in terms of body weight and payload, and for example, body weight and payload, for example, this is a straightforward problem for us, because normally when you have a mobile robots, for example, if I take an ant, for example, an ant, small ant, it can carry 8 times the body weight, its own body weight, compared to robots. Right? For example, if I design a robot manipulator, the maximum, the normal way of design now, we can only, the payloads only at not more than 1/10 of the 1/10 of the weight of the robot itself. So so you can see that the weight payload constraints are very critical when we talk about autonomous mobile robot design. So in terms of making decisions, for example, there are many angles that where there are many limitations in our computing capabilities in terms of the parallelism or collateral co-processing of the ability to make very fast decisions. When we use AI, we use machine learning, there's a lot of data coming into our processes. But how do our processes manage this data? And so this is where sometimes when we look at in nature, when you look at how, for example, insects execute their navigation, flight navigation, for example, making, for example, bats, insect, or if you look to bigger organisms like bats, for example, how it can fly very fast in a very dark cave without hitting the wall of the cave, for example, using sonars, using very fast decision making, very flexible, for example, ears of flexible cone, acoustic cone, in order to ensure that it can fly very fast and make fast decision. So these are very real challenges when we talk about now, for example, in the mobile robot communities, they talk about swarm intelligence, swarm robotics, or multi-agent robotics, where when we, in order to execute a task, instead of sending one robot, we send, let's say, 20 robots or 30 robots with the same mission or with the same task that it needs to complete. So we have learned from nature that the concept of redundancy, that means the system may be simple, but because we have many robots trying to achieve the same goals, it increases the chances of success, the success percentage of the mission. So these are some examples where nature does it so widely. That means in terms of the issue of redundancy, in terms of ensuring that if one robot fails down, there's the list or the sequence of robots, other robots which can assist in order to complete the task. So these are some in terms of things that we can learn in terms of how we program our mobile robots, especially when we have a multi-agent or we have multi-robots deployed in order to execute the same task. So because we need to ensure that at the end of the day, we need to ensure that the tasks are completed. So and we know that there are many designs which have been inspired by nature. You know, Velcro. These are very years we are using Velcro. It is designed by from the plants that tend to stick to our clothes, to our trousers. So this Velcro concept. So Velcro, you know about gecko feet of the gecko that it can stick, and it has very fine structures under its feet in order for it to stick to walls, for example. So these are many examples that we can get from nature in order for us to ensure that when we design our autonomous mobile robots, we are not just we always look at the nature and how does nature does it. How does nature solve that particular problem? Of example, climbing vertical walls, for example, or sticking to the ceiling, for example. So those are some of the ingenuity invention of nature's tiny things or tiny tools that we can get inspiration from. So we talk about, as I said, we talk about redundancy. So having tens or even hundreds of parareceptor cells, for example, improve the signal-to-noise ratio through averaging. So this is, and in terms of when we talk about swarm intelligence, this is where we deploy multiple, more than one robot. As I said, 10, 20, 30 robots in order to complete the same task. So this is where how you optimize in terms of its the swarm deployment algorithm, for example. So this is a real example of redundancy. Yeah. So so that we ensure that at the end of the day, the task will be completed. Okay. So when we talk about biomimetic design or biomimetic or bio-inspired design, so we talk about concepts, getting concepts from a non-engineering domain such as biology, from bacteria, plants, insects, mammals, reptiles, and the likes. The way that they adapt to the environment, and the way that, for example, the elegant methods of sensing, communication, all these are what we call biomimetic design or bio-inspired design. So when we talk about mobile robots, you have what are the fundamentals module, or what are the fundamental elements of a mobile robot. So you have, of course, you have the sensing modules, you have the power modules, you have the control modules. Of course, you have the vehicle design or platform design. You have the communication modules, and then so these are different modules, which each one of them we can get inspiration from nature, from how nature does it. For example, in terms of the manta ray, for example, manta ray, in the ocean manta ray, it has a very wide, very big wings on the side, and it has the way of undulatory motion. It doesn't, of course, it doesn't have propellers, but it has the flexible wings that by the flexible motion of the side of the wings, it can change, it can propel itself in the water and change direction. So, which is very effective, which is very energy effective, energy efficient compared to us when we want to move, let's say, our submarines, for example, in the water. We are using propellers, and we have to convert rotational motion in order to have linear propulsion. So this is immediately a waste of energy, converting rotational motion, trying to get the derivative of linear motion. So this is very loss of energy in terms of the energy usage. So you can see when we talk, like myself in our team, when we designed our mobile autonomous underwater vehicles, we would like to see how, rather than using propellers, using motors, we use different methods of propulsion. Single undulatory or single what we call it, fins on the sides, flexible fins, for example, and those are the kind of things that will be able for us to be able to ensure that we can move, the robot can move. Of course, we have when we talk about biological system, it offers exemplary methods for flight, imaging, sensing, adaptation to environment, locomotion. So we know that we engineers have learned from this and created many technologies. For mobile robots, I think mobile robots, autonomous robotic platform community, research community, we have utilized many of the biological system inspiration models in order to solve many of the problems in terms of, for our research group, we talk about designing the robotic platform, designing the propulsion method, the sensing method, how we make sure that when our robot are put into the water, it won't be flooded. The electronics will not be flooded. It is enclosed properly, etc., etc. So there are many things that we have learned, that we need to learn from the environment. So I think one particular angle that our team have developed is developing the acoustic sensors in order for us to, based on the pressure change, in order to know to assist the navigation of our marine robotic platform. So you can see here we have there are a number of things that we have done that we can get, for example, from the biological sensor methods, how nature sense the environment, and then we adapt it for our particular application. So now back to marine autonomous vehicles. For marine autonomous vehicle, it's a very learn. There are many angles that constrain when we want, for example, if we want to deploy the robot in the oceans, for example. So there are many constraints. So this is where we look into nature. How does nature solve it? So for this particular, if you can, I'm not sure whether you can see the picture. You can see the picture there. This is what we call an autonaut. The picture on the autonaut is basically this is a long-term deployment autonomous robotic platform that can be deployed for long-term out in the oceans. For this particular autonaut, it can be deployed up to I would say up to 3-4 months easily, because it doesn't need changing of batteries. It is using purely the wave energy. In order the wave energy, as long as you have the wave moving, that wave has been harvested. They harvest the energy wave in order to propel the autonaut forward by using foil, a flexible foil at the back and at the front side of the platform, in order to convert the vertical motion to horizontal motion. So these are example of where instead of using propellers and you try to convert rotational motion to a vertical horizontal motion propulsion, this is directly harvesting the vertical wave and using foil in order to induce propulsion to the craft, to the robotic, to the platform. And you can see there on the platform you have some solar panels. Those solar panels are only to recharge the electronics for communication, etc. And it is sufficient. So in terms of propulsion, it is purely using the wave energy. So this is a clear example of how, instead of using man-made straightforward using a conventional solution, we look into the nature and see how does nature does it. So foil, flexible surface that will induce motion is the answers in this particular case. So you can see this is just to show that there are many applications for ocean autonomous robotic platform, in particular marine robotics. As I said much earlier, fundamentally the design of bio-inspired robotic platform are very similar, but once we have decided the environment where we want to deploy the robot into, then we have to tune back our solution in order for the mission to be success. Okay, so I just want to show, I think I'm running I'm already about half an hour now. So for our I just want to share one project that we have done. So this is what we call a micro-autonomous underwater vehicle for coral reef inspection. So where we use a fuzzy robust filter control technique. So I just want to highlight that I know that my talk tonight is this evening is about bio-inspired design. So when we talk bio-inspired design, we are talking about in the bigger picture, not just on the sensing design, but of course on the navigation planning, on the obstacle avoidance, on the decision making, on the localization method, etc. Those are all can be considered as a bio-inspired kind of approach. So for our particular this particular project, we were trying to design a multi micro AUV. AUV is what we call an autonomous underwater vehicle. In order to map our coral reefs. Malaysia, for example, we are part of the coral triangle countries. We have many coral reefs, for example, because we are near the equator. So we one. So we use this design and we have cameras on board. So if you look at here, we have cameras on board and also all the electronics on board. So it's a three-fin kind of robot. But in this particular case, we did not use flexible wings, but we use propellers. But in this particular example, it's not an issue because we are trying to just do the coral reef mapping. So you can see these are, we have done the design specification, we have the prototype design, we did the prototype modeling for the control, and we fabricate it. So it's about, this is the design of the robot, and we have the control specification, etc. We use a robust control approach, and these are the electronics. So we use this is one. It's a very low cost kind of a micro AUV. So AUV, and we use a number of these, and we deploy it as a team, and it goes as a team and do the mapping. So this is what, because when we talk about fish colony, etc., it always goes in groups. In schools, it doesn't go alone. So in order to complete one particular mission. So this is an example, the things that we have done in order to ensure that when we design the fin, the angle, etc., how much force, how much effect it has on the propulsion that on our robot. So it is very interesting. I think we have managed to develop the micro AUV system to work in a swarm. It's a swarm multi-agent kind of deployment. We have managed to develop very stable, robust social control technique, and it has been deployed successfully. So I think I will stop at this point, Rustam and listeners. So very short and I would say overview of the approach that we have taken. So I think in terms of the conclusion, I think bio-inspired autonomous robotics are the future for many critical applications. The design and development of robust bio-inspired autonomous robotic platforms, of course, require knowledge in mechanical platform design, material selection, electronic control modules, communication modules, power modules, and the overall hardware software co-design framework. So when we talk about bio-inspired, we are not just looking on one particular aspect. We're looking at the overall, all the sub-modules put together and optimize it. And for the marine sectors, what the focus of our research group, the exploration and exploitation in deep oceans require state-of-the-art technologies covering many aspects. So bio-inspired approach may provide many cost-effective solutions. And of course, finally, the use of hybrid sensors, energy harvester module, AI, machine learning, and long-term ocean deployment will be among future criteria of marine autonomous robotics, especially bio-inspired marine autonomous robotics. So thank you very much. This is for listening, and I shall stop at this point, and I hope you will you have benefited somehow from my presentation. Thank you very much.
Okay, thank you very much, Professor Arshad. I would open it for questions. So if nobody has a question, I will pose a question. It's very interesting topic about the marine robotics, yes. Marine underwater robotics. Yeah. Also, you try to mimic marine animals to create these robots. What are the major risks of such robots? What kind
major risks?
Yeah. Yes.
Oh, okay. So maybe I would say challenges. I would say challenges, issues, maybe challenges or issues.
Yes, challenges, issues. What?
Yeah. The problem with us when we design it, normally researchers will only look at one particular aspect. For example, when we talk about trying to mimic the propulsion method, we only look at the propulsion mechanism, but we have trouble trying to find the right material to produce the same propulsion, the same rate of motion, for example, shape of motion. So those are, so that's why, and then there's an issue of signal processing, how fast you can process. Because for manta-ray, for example, if you want to mimic the wing of the manta-ray, it has many muscles and it has many, you need to process a lot of information. So So I think the challenge is that when we go and design a bio-inspired autonomous, for example, in this case, marine robotics autonomous platform, it needs to be looked at from many angles, not just on one particular aspect. For example, not just on the propulsion, but also on the energy management, on the decision making, on managing the signal processing to make decision. Because I always find, even in our research, sometimes we only focus on finding the right material. Now, once we find the right material, we realize that we have not solved in terms of the power usage. So it's always the optimization of the design approach.
Okay, thank you very much.
Okay.
So if there are no other questions, I will start my presentation.
Okay. Thank you, Dr. Rustam.
Yeah. So do you see my presentation?
Yes, yes.
Does it run?
Yes, yes.
Okay, thank you very much. So, hello everybody. I will give a presentation on approval of autonomous trains. My name is Rustam Tagiev. I am from German Center for Rail Traffic Research as a Federal Railway Authority. I am scientific desk officer. So our center is founded in 2019, and since the last year I started to work there. So, like most of the staff, the tasks are contract research, application research, and own research. So we are a departmental research facility, in Russian ведомственная научная исследовательская организация. So we are part an authority and partly a research agency. There's a disclaimer I wrote here. My presentation does not represent the opinion of authority, which is part of German administration. So it's just my own opinion. And I would our goal of our organization is to connect politics, industry, and science, and push it forward. The autonomous trains have the trains where the computer vision replaced the human one. So there are many levels of automation. The norm, which describes this multiple levels of automation, is called the IEC 62267, and it's for automated urban guided transport. It's so there's a difference between the railway transport of urban and non-urban, but the level of automation apply for both. So we have GOA as a grade of automation 0 to 2. This is just there's a in-cabin human perception required, so there's always a person sitting there. So on the highest GOA 2, the person doesn't do anything; it just observes the machine working. And then the GOA 3, the driver can also walk through the train and check the tickets, for example, and the train goes by its own. And GOA 4, there is no person at all on the system. It can the remote control is independent of this machine perception. It's just a kind of fallback system for the machine perception, but it's on the other side also the machine perception can be a fallback system for the remote control. So in the actual case, you have a central control of the autonomous trains, and there's one driver responsible for many trains, and some trains allow attention, so some trains require attention, and it's reported from the machine system. So both systems are a fallback system for each other. So now we go forward and try to understand how such a system, such an autonomous train, is built. So we have the human perception by eyes, which is replaced by computer vision, which is not only cameras, it can be also some radar, ultrasonic, infrared, LIDAR, and so on. There are many sensors. It's not just visible information. It's not just the eyes. And then we have also the collision detection. So it's in the case if the train goes at night, there's a collision, the driver will not see it, or out of some reasons, but he might hear the noise of collision, and he has to stop the train. And there's also the so-called seat of the pants field. So if something wrong with the rail, the driver will notice it and has to stop. So these are two major modules, and the planning and execution is not so complicated in case of rail, because you cannot dodge anything. So it's just stop or accelerate. So it's not so complicated as in case of driverless cars. So we have, as I already mentioned, the situation in case of a railway is different to the cars. So dodging is not possible. Braking distance often longer than visibility. So if the driver sees something, it's already too late to avoid the collision. Emergency braking cannot be aborted in most of the cases. So if the driver starts the emergency braking, the train will brake until it's stopped. There's no standard, and there's also no standard for wireless signal transmission or vehicle to infrastructure and so on. So it's not everywhere. At some connections, the signals, so the prediction of some trains on the track, and where the train has to stop, it will be transmitted, can be transmitted to the vehicle. The GNS and localization is almost not existent. It has to be built in for autonomous driving. Digital map is also not standard. It does not appear everywhere. So the obstacle detection and collision prediction has to replace this. Might have to replace these systems. Collision detections: the rollover, frontal collision, side and rear collision of the locomotive, side and rear collision of the wagons. It's all still in early research. For the rear collision, so the driver doesn't notice if something in a right train, freight train, the driver doesn't notice if something goes wrong with the wagon, with the 100th wagon in the rear. So it's still in the early research to build such a system which can detect a collision. Before autonomous trains can be operated, they have to be approved and certified. There's a regulation. It's a SMRA. There's a risk is determined by the number of fatalities per hour. The assessed risk has to be lower than the accepted risk of the reference system or the harmonized design targets. So far for the approval and certification, we have to count how many fatalities can appear through this system. And for commercial operation, there more other risks like environmental damage, number of injured, so it's different to the number of fatalities, material damage, which is also a financial matter of cost, and also financial damage. So this is a different topic. So before we go to the operation, we have two ways. So in the legal regulation, we have two ways how we can approve a system. The one is the explicit risk estimation. So the number of catastrophic accidents where more than one fatality appears has to be 10 power minus 9 per operating hour, and critical accidents, one fatality, 10 power minus 7 per operating hour. So this failure rate has to be proven concerning random errors, and these failure rates have to be kept under control. So we have a special software approval norm for 50,128 and 50,657, where the risks of the software are defined in a normative way. So we started to free, even free projects. We awarded them. So the project ATO Sense is a functional requirement assessors or logic of ATA unit. It focuses on actual human abilities. So what is an additional way in the norm to in the legal regulation to approve the system? So either the system has less fatalities than what I said already before, or the system is better than is as good as a human. So the one project has to calculate the risks which come from the human driver. The second project has to calculate the acceptance of the autonomous driving and detect the system boundaries, which also very important. Like if the driver sees a crime happening inside of the train, is it the task of the actual system to detect this crime and call the police? Then there's a third project which will end next month, and there will come a list of standard sensors, or list of standard sensors for this for a autonomous train. Now we can make the system a bit more subdivided in a bit more modules for the computer vision. So I did not include in this graph the collision detection. So there's noticing when the collision already is there. In the case it's already the damage is there. So I just took the computer vision, because here we have CV Hazer by the Austrian Institute, AIT, and they subdivide the system into this environment where we have light sources, object, obstacles, and medium, which is connected to the camera, and the camera is gives the information, gives the raw images to the segmentation and the scene reconstruction. This is just let's say typical design of the system. And then there's also planning and execution. So to assess the risk, we need some kind of modularization and this is a more detailed modularization. According to the norm of software approval for vehicle software in railways, we cannot use typical algorithms for machine learning. They are not mentioned there. So, and without machine learning, we cannot actually implement reasonable computer vision. And there's also an automotive norm specification, ISO pass 21448, and there's written verification and validation of automotive perception is difficult. So the verification and validation is a way it's done till now with conventional software on the vehicles. So we have the design. So this is this typical V, because we both have the V, and it's just this way of depicting it. We have the design of the full system, we have design of subsystems, and we have implementations, and we verify the subsystems, and validate the subsystems, and then we validate the full systems, and we can only imagine how it can be done for machine learning. And now we have also a norm specification for machine learning, especially the deep learning, which is needed for computer vision. It's a DIN spec 13226, and the terms used there are different as in the automotive norm. Why? Because the one usage is from AI, from statistic, and the other term usage is from engineering science. So what are the differences? So verification, as a known, is testing the system on known data. So we have training data, validation data. So in AI usage, you take the training data, train your architecture, and then you validate the architecture. And if your architecture is not good enough, you choose another architecture and then validate again on the validation data. Validation in the engineering sense is testing on unknown data, and it's only once. So it's for us the test data. So here we test it only once at the very end of the, just to calculate the failure rate. Verification in the conventional software is just you have to read the code, so normally, but you can do it in case of deep learning, neural nets. You cannot read them by experts. So you need then somehow make them readable. So in order to do something similar to this conventional way. So there's something similar is this explainable AI. So you take this picture, it's recognized as a locomotive. It's not a locomotive, but you can see because of the tracks and because of this some boxes, a box on the tracks must be a locomotive. So it's you see on this picture how the system actually understands, and that's what the best thing, what the best you can do for deep learning systems is to analyze such pictures, such level-wise relevance propagation pictures. Now we need, of course, a lot of experience to establish such verification by explainable AI, and then we need a lot of open data sets. So for road vehicles, since 2006, open data sets are published. I count something about 60 bigger data sets for road traffic, and there are only 2 data sets for rail traffic. So it's rail traffic left behind. What is actually such a So those two data sets. The one is RailSem 19. This is the left. So there's a picture of the tract, and this is the annotated picture of the tract. This is the so-called semantic annotation. So everything is annotated. And there's FR sign, the right, is the French data set. It's you see the picture of the again the picture of the rail scenery, and you just have boxes around the signals. So in French industry seems to think that it is important to read the signals instead of transmit them by wireless communication. Okay, it's an interesting stance. So you can read more about. Actually, have a table of these data sets on my website. So just go into here, and you will see a table of them. The problem with deep learning is that if we take a data set, and in the data set we have clusters, and from every cluster we take one out for validation. Validation is the AI sense or cross verification. So then we don't have any problem. But if we exclude one cluster from the cluster, then we have problem, because it has to extrapolate, and extrapolation is not that good for, it doesn't work that good on neural networks. So we have this we have somehow to call on to understand the special cases. We have you can give them many names. Sorry. So you can give them many names. So the common case, incorrect data, or something else. So the terminology is still not clear about them. So the subsystems validation. Now we try to validate. So we can as the validation. It's so you take the computer vision system, and you validate it on pre-recorded data. With synthetic data, like the car environment in the case of cars, is not reasonable, because synthetic data does not really prove it. How can we do it? We have to create a platform where different companies giving their data. So the company whose system has to be validated have not seen this data before. So this is a very important point in the case of validation. So we have we need a taxonomy of possible edge cases and corner cases. Then we have a list of tasks and obstacle types, and we need a standard sensor set, because every company has a different sensor set. We will have different data sets, and we cannot cross-validate them with each other. Then we can take the system and validate it on just in the real environment with a human supervisor, and we can validate it with drones. So we have a drone flying from the top ahead of the train, and then they validate what the train and the drone doing. We can validate the internal parts of the system by synthetic data. So this is the validation of the validation of the full system is millions of kilometers, which is like the very, very last step in the validation. We have some certain risks. So now, after the validation, what we will have is a probability of malfunctioning. And what can we do with this probability? We still have to define: is it low or is it too high, this probability? So we have to go down to every detail of the train application, and just to find out what can happen. I just took the case of frontal collision. It's not the collision from the side, from the rear, or something else. There are many cases of where the system has to react. I just take the front collision. So we have two columns. So the column braking distance is shorter than the visibility. So you can, in this case, you have to avoid the collision. So braking distance is longer than visibility, which is mostly the case. Then you have to delay. Oh, sorry. You have to delay the collision. So even if you collide with something, delaying collision can save lives. If there's a car on the track, the driver can jump out in this moment and delaying collision. So braking ahead is good, and reduction of collision energy is also important, and as well as danger zone. So around the trains, there's always a danger zone. The faster the train, the greater is the danger zone around the train, and slowing down is also good. Even if the train has collided, this happened once with a human driver. At night, the human driver collided, the train collided with a human, and then the train came into the station with parts of human body, and was not very okay. It was bad. So preventing the collided train from moving on is important. On the other side, avoid of unprovoked hazard braking. So if there is something the system thinks it has to brake, it puts on danger the passengers to certain extent. And in case of suicide, it's even not recommended to brake hard, because it will not save the life of the suicide, but will put the passenger under risk. Just take a very this simple example. So we have a car, and let's say it's like 600 meters to the car, and the braking distance on this track is 650 meters. So at some point, it goes clockwise. So at some point, the driver has to detect the car. The same applies to the computer system. So at some point, it has to start braking, and we have to calculate this curve, the probability density. At which point, so this is kind of hypothetical curve. So it's for human drivers, it looks like that. For computer systems, we still don't exactly know, because they will have we have to measure them, and the mean appearance of braking is somewhere here, for example. Now, what can it make? According to, so let's say the train goes by 130 km/h, visibility is 600 meters in the curve. So the radius of the curve is 15 kilometers. And the braking is 1 meter per second cube. So there's a kind of green area. So if we have the speed and we have the visibility. In this green area, the braking will save the life of the car driver, because according to the norm, if it's lower than 40 km/h or lower, he will not die. It's just written there. It's kind of experience, and we are in the green area, but we are very short in this green area, because if the driver recognize, if the train driver recognize the car bit later, the car driver might die. if he stays in the car. But if the driver, car driver, notices the train and jumps out of the car, he will stay alive. And let's assume that 200 meters ahead of the train, the driver realizes that the train is coming because of the noise of the braking, because of the whistling of the train, and so on. And if the train starts to brake earlier, he will need less seconds for the last 200 meters till the driver, and the driver has more time to run away, to jump out. As well as danger zone is smaller. So this is from the middle of the track. So it's 190 centimeters, and that is 230 centimeters at 130 km/h. So if he doesn't get blown into the train, because the train has some wind around it, and can get into the train because of it. So as you see, the approval of autonomous trains, I have to agree with the previous speaker. We actually create railways, animals, and we have to think about like everything. So approval of autonomous trains here in the middle has to do with a lot of topics. So it's computer vision, and it's the computer vision needs some simulation for generated pictures, and it needs also some cybersecurity, and open vision data sets are important, and there must be a large consensus around of developers, which can bring to technical norms, and we also have to think about why we need autonomous trains at all. And we have also at our center we have a legal expert. He advised me in all the regulations. So without him, I could not get into this area. We must also think about the train driver who will not sit in front of the train, but who checks the tickets. But just in emergency, he has to go to the train and check the system. So there is also some demand for staff education. AI for the validation of deep learning, we need a AI platform. Maybe we need special sensors additionally to the standard sensors. We have to develop further explainable AI. Computer vision also, for the computer vision, we have some complicated risk calculation. And for risk calculation, maybe we can reduce the risk by digital map of vehicle localization, which is not yet on the vehicles. Train control systems, which are also the connection between the infrastructure and train, remote control, trackside sensors. Maybe at some points of the tracks we need sensors to sensor something ahead of the train. Conditions for social acceptance also is an important thing. We have some regulation now, but maybe they can change because of some political change, since once the society is aware of autonomous trains. Behavior prediction, also a topic. So if there's a human, we have to distinguish a suicider from a trespasser, from somebody who doesn't understand the risk. So the one who involuntarily gets him into risk, and the impact detection, as I already said, is now under research, is in early research. And well, maybe even some non-deep learning vision, since deep learning is very difficult to validate or to calculate any risk of it. So so far I am done with my presentation. Thank you very much. So I am open to questions. Так, я ничего не слышу.
Вас слышно.
Меня слышно. Так,
Да.
это я понимаю. То есть от вас пока никаких вопросов не идет. Понятно.
Maybe Kamal have a question. Kamal,
do you have a question? Вы можете на русском, в принципе.
Может быть, просто у Камала есть вопрос, он на английском общается. Вот в чате есть исследователь из Малайзии.
Окей.
Камал, if you have question, you can ask. If not, we go next.
А он пропал, из Малайзии он пропал, отключился.
Хорошо, тогда продолжим, тогда получается так.
А он отключился. Его нет.
Да, у меня единственный вопрос к Рустаму. Да, вот хороший доклад это, во-первых, а во-вторых, относительно распространения. Как я понимаю, это применяется, вот эта система только в Германии? Или это предполагается распространить на другие страны, ЕС, например? Или, может быть, даже шире?
Ну, я сейчас делал исследования из немецких законов, но по этой системе Россия впереди. У вас там вокруг на Московском этом кольце уже есть поезд, даже ожидается, что его через пару месяцев уже разрешат, то есть который автономный поезд. Это не единственная фирма.
Ну хорошо, а вопрос вот такой вот, ведь автоматизация любого такого рода, которая связана с массовым транспортом общественным, она несет в себе риски, да? Риски в том числе связанные с, одно дело это, испытывают даже автопилоты на автомобилях, да, и там возникают множество проблем, связанных просто эффективной координации на дорогах, да, между ручным управлением и автоматическим. И ручным имеется в виду, когда человек управляет автомобилем. И то есть множество проблем, там, начиная от технических и заканчивая какими-то морально-философскими, да, типа на ком будет ответственность, если на автопилоте автомобиль собьет, да, пешехода, например, да? Кто несет ответственность? Разработчик, водитель, который позволил именно перейти в автоматический режим управления, или пешеход, да, кто виноват. И таких однозначных ответов нет. Это дискуссионные вопросы, они обсуждаются активно. А в железнодорожном транспорте, да, там с одной стороны просто, там не так много пешеходов, как в случае автомобильного транспорта. И в принципе там довольно такая автоматизированная система, это понятно, да, но тем не менее предусматриваются какие-то системные подходы, которые могли бы снизить риски. Да, все-таки автоматическое управление, тем более поездом, это высокорисковое дело.
Мы снижаем в железнодорожном транспорте, мы снижаем риски буквально всеми возможными путями. То есть на самих рельсах есть датчики, которые замечают, сколько проехало там этих осей то есть и сколько выше, то есть из каждого, то есть такая даже уже давно, уже несколько десятков лет назад уже были системы, которые регистрируют, сколько осей прошло через определенный участок. И сколько там осталось, сколько попало на новый участок. Если там остались оси, то зажигается красная лампочка и не проезжает поезд туда. Ну, в принципе, уже настолько все развилось, что поезда высокоскоростные. Там человек, он ничего, кроме как следить за машиной, не делает. Он просто сидит и нажимает на кнопку. И только когда происходит очень редко что-то внезапное, что-то непредсказуемое, он только тогда должен нажать кнопку «тормозить».
Хорошо, последний вопрос. Он вытекает из ответов ваших. Но в случае автомобиля, да, там очень много разработчиков и именно среди корпораций, да, и Google, и Tesla. А все-таки, если говорить о железнодорожном транспорте, да, там прерогатива, как я понимаю, остается за государством, да? То есть, или все равно есть, например, условная какая-то корпорация, которая создает такие системы. То есть к чему такой вопрос? Кто будет нести ответственность, да, в случае какого-то сбоя, соответственно?
Ну, понятно, как его. Ответственность в случае сбоя обычно несет в первую очередь тот, который разрешил, как бы сказать, со стороны государства применение этого определенного нового устройства. А он должен защититься тем, что это устройство, в принципе, отображается в нормах. То есть есть технические нормы, которые, как бы сказать, то есть он не знал лучше. То есть в суде, то есть если он не знал, по-настоящему может доказать, что он не знал лучше, а следовался общепризнанными нормами и так далее, то тогда никто не виноват. Тогда...
Начнем. Значит, в промышленности часто используются, все чаще начали использовать различных роботов и манипуляторов, как последовательные, так и параллельные структуры. Механизмы параллельной структуры по сравнению с механизмами последовательной структуры имеют ряд преимуществ, таких как точность позиционирования, повышенная эффективная грузоподъемность, быстродействие, плавность хода и еще некоторые. Одной из важнейших задач при проектировании роботов и вообще организации производства является определение их рабочего пространства. Основными методами являются геометрические, дискретные методы интервального анализа. Геометрические и дискретные методы имеют ряд недостатков. Геометрические сложно использовать для сложных пространственных роботов, а дискретно не позволяет получить рабочую область с высокой точностью аппроксимации. Мы использовали один из методов интервального анализа является метод неравномерных покрытий. Аппроксимация множества решений систем нелинейных неравенств или уравнений. Составляются неравенства или уравнения, вычисляются минимумы и максимумы функций левых частей. Для систем неравенств, если минимум хотя бы одной из функций больше нуля, то такой интервал исключается, то есть он не входит в рабочую область. Если максимум всех функций меньше либо равен нулю, то параллелепипед вносится в рабочую область. В остальных случаях делится пополам. И это происходит до тех пор, пока не доходит до определенной точности аппроксимации. В случаях систем уравнений нет условия, для систем уравнений нет условия для внесения в рабочую область, а условие исключения является значение минимума хотя бы одной из функций больше нуля или значение максимума одной из функций меньше нуля. Полученное в результате моделирования, в результате метода неравномерных покрытий, покрывающее множество параллелепипедов преобразовано в множество параллелепипедов вытянутых и упорядоченных по возрастанию. Так, далее. Мы рассматриваем робот параллельный 3PRR механизма параллельной структуры, то есть эта структура имеет 3 кинематические цепи, имеет одну прямолинейный двигатель и 3 вращающихся, одну прямолинейную кинематическую пару и 3 вращающиеся кинематические пары. На этом слайде представлены основные кинематические соотношения, уравнения прямой и обратной задачи кинематики, а также ограничения геометрических параметров. На этом слайде представлены результаты моделирования для этой структуры робота. Критерий оптимизации выступала рабочая область с учетом пересечений. Вот на первом изображении изображена рабочая область с учетом пересечений и ограничений, а чуть правее область именно самих пересечений, где не может достигнуто быть положение. Снизу визуализированы сами звенья, то есть показаны, какие могут быть пересечения. Так, значит, исходными данными у нас являлась рабочая область, полученная рабочая область в виде упорядоченного множества целых чисел. Интервалы чисел по одному из измерений образуют параллелепипеды, длина которых соответствует длине этого интервала, а размеры по оставшимся 2 измерениям у каждого из параллелепипедов равны, зависят от точности аппроксимации. То есть вот представлена рабочая область в виде параллелепипедов исходных, а справа показана эскиз, то есть как они вблизи, то есть вот эта модель, она разбита на множество параллелепипедов. Так как модель для визуализации была экспортирована в формат STL, который подразумевает разбиение объектов на треугольники, такая вот модель полученная имеет очень большой вес, то есть множество объектов. Каждый параллелепипед имеет 6 граней и, соответственно, 12 треугольников. И если все параллелепипеды визуализировать, то это будет очень объемная модель, с которой очень сложно работать. Из этого вытекает проблема оптимизации и уменьшения количества этих составляющих объектов для дальнейшей работы с ними. Хотелось бы отметить, что было проведено исключение из этой модели внутренних поверхностей, которые находятся внутри рабочей области, и была выявлена только оболочка, ну, наружная поверхность рабочей области. И с плоскими поверхностями гораздо проще работать. Первый подход мы будем рассматривать для примера плоскую поверхность, для того, чтобы как-то проще объяснить сам подход. Подход заключается в поиске максимального количества непересекающихся отрезков, соединяющих вогнутые вершины рассматриваемой исходной области. Ну, если быть точным, то мы ищем в первом подходе минимальное количество прямоугольников, которые включают в эту область, то есть перераспределение данных. Формой представления пересечения отрезков принимаем двудольный граф. Следовательно, точнее не следовательно, а задача в этом стоит найти максимально независимое множество двудольного графа. Дальше у нас представлен алгоритм преобразований, как мы поступали. Сначала определяли граничные точки каждого параллелепипеда, затем определяем вогнутые вершины. То есть вот на рисунке вогнутые вершины показаны черными точками, затемненными. Далее мы находим всевозможные соединения вогнутых вершин горизонтальными или вертикальными отрезками. Таким образом, все отрезки соединений принадлежали рабочей, чтобы все отрезки принадлежали рабочей области. Вот они справа на рисунке изображены. Далее, если отрезки пересекаются, мы составляем двудольный граф. То есть, если они пересекаются, то между вершинами графа есть соединение. Так. Поиск независимого множества. Для поиска независимого множества мы использовали метод поиска в глубину, который используется в теории графов. Поиск в глубину заключается в том, чтобы последовательно расширять независимое множество, двигаясь только по одной ветке дерева. Обход можно начинать из любой вершины, множества. Если вершина смежной, если вершина имеет только одну связь с другой вершиной, то на первоначальном этапе есть смысл удалить вершину, с которой она соединена. Таким образом, мы уменьшим количество итераций, количество обходов. То есть перед каждым спуском на уровень ниже в дереве графов мы проводим поиск вершин, у которых только одна связь с другой вершиной, и удаляем другую вершину. И поиск ведем до тех пор, перебираем все возможные варианты. Поиск останавливаем на том моменте, когда, допустим, мы идем по одной ветке дерева и останавливаем поиск в тот момент, когда мы уже знаем, что дальнейший спуск ниже не имеет смысла. Допустим, мы нашли лучшее решение в какой-то другой ветке, и уже можно дальше не искать. После нахождения независимого множества, то есть наших ограничений, можно приступать к перераспределению данных. Мы исходные параллелепипеды перераспределяем в многоугольники, в качестве ограничения выступают вот найденные наше независимое множество двудольного графа. Далее мы полученные уже многоугольники можем, если в них присутствуют еще вогнутые вершины, мы можем их разделить либо по горизонтали, либо по вертикали. От этого результат не изменится. И завершающим этапом, так как формат STL предполагает, что объект будет задан в виде треугольников, мы разбиваем прямоугольники на треугольники. Таким образом, наша модель не потеряет точность, а вот количество полигонов и объектов уменьшится. На этом слайде представлены результаты применения алгоритма на стадии разработки. Слева показан случайный контур, а справа контур после того, как мы применили на нем алгоритм. То есть видно, что количество объектов уменьшилось. Вот. И результаты в зависимости от сложности контура могут быть разные. Так, второй подход преобразования. Мы рассматриваем триангуляцию Делона с ограничениями. Триангуляция Делона называется такая триангуляция, в которой для любого построенного треугольника верно, что внутри описанной около него окружности не находится вершин из исходного множества. Для невыпуклых четырехугольников условие Делона всегда выполнено, а для выпуклых четырехугольников, вершины которого не лежат на одной окружности, существует ровно две возможные триангуляции, одна из которых является триангуляция Делона. Вот на рисунках представлен алгоритм перестроения, о котором сейчас я дальше чуть расскажу. Вот стоит обратить внимание на углы альфа и бета, которые вот как раз участвуют в проверке условия Делона. Для любого треугольника триангуляция условия Делона будет выполняться только тогда, когда для любой точки этой триангуляции, принадлежащей, будет выполняться условие, что углы альфа и бета меньше либо равны 180 градусам. Ну и в дальнейшем, и далее вот расписанные уравнения, которые мы использовали Данные вычисления требуют непосредственно 10 операций умножения, а также 12 операций сложения и вычитания, что положительно сказывается на вычислительных мощностях. Ну и сам алгоритм триангуляции Делоне. Сначала мы строим треугольник, одна грань из которых обязательно должна лежать на границе области. Дальше от каждой вершины исходного множества мы строим новые треугольники. И строим новые треугольники. Далее необходимо проверить условия, не пересекаются ли треугольники, новые получившиеся, с границами области исходной рабочей, либо если они пересекаются с другими треугольниками, то такая точка откладывается на последующие решения. Если треугольник построен, то необходимо провести для этой триангуляции проверку на условия Делоне. Если условие не выполнено, то этот треугольник перестраивается, так как мы говорили выше, что для любого четырехугольника существует две триангуляции, одна из которых триангуляция Делоне, это сделать несложно. И алгоритм повторяется до тех пор, пока не будет возможности построить очередной треугольник. Так, здесь представлены результаты моделирования, то есть слева вот наша исходная область, которую мы вот рассматривали для примера, а справа область, которую мы рассматривали на этапе проектирования. Тоже случайный контур и сама триангуляция. Что касательно робота параллельной структуры, то эти алгоритмы были реализованы на языке программирования, чтобы ускорить этот процесс, и были использованы также параллельные вычисления. Если касательно первого подхода, в котором мы искали наименьшее количество прямоугольников и поиск в глубину, где использовали, там параллельные вычисления использовались на этапе поиска в глубину. То есть каждому потоку ядра, да, ему сообщалась своя ветка, и он шел по этой ветке до конца. Да? Вот. А что касательно триангуляции, то каждая плоскость, наружной поверхности, каждую плоскость, каждому потоку давался объем данных касательно именно этой плоскости, и уже в процессе работы выполнялась сама триангуляция. Так, сравнительный анализ. Значит, вот полученная исходная рабочая область имела 50 тысяч граней в 3D-модели. После первоначальных преобразований при вычитании внутренних поверхностей количество треугольных граней значительно снизилось до 6000. И после преобразования и первого и второго подхода еще снизилось примерно в 2 раза. То есть вот для первого подхода это 1994, для второго 1972. Изначально мы беспокоились, что такие алгоритмы достаточно ресурсозатратные, однако, так как плоскости моделей имеют достаточно простой контур, не имеют внутренних полостей, такие подходы достаточно быстро работают. Вот можно сказать, что с исходной рабочей областью количество треугольников уменьшилось на 96%. Что касательно будущих работ, мы предполагаем провести для триангуляции либо объединение треугольников, либо какую-то селекцию этих методов и использование хороших сторон обоих методов и поиска минимального количества треугольников для визуализации модели. Вот. Спасибо за внимание. На этом все.
Так, спасибо большое. Вопросы?
А какой язык использовался для написания?
C++.
Угу. А какие-то программные пакеты использовались уже существующие, прикладные?
Нет, не использовались.
Угу. А, соответственно, вот вы упомянули высокопроизводительные вычисления.
Ну да, использовались OpenMP, да.
Да, окей. А, соответственно, какие мощности были использованы, если мы говорим о высокопроизводительных вычислениях?
Вы имеете в виду про...
то есть на чем вы считали, да? Обычно такая ресурсно-затратная вещь, она не дешевая.
На удивление, мы думали, что будет больше ресурсов затрачено, хотя алгоритм достаточно быстро считался. Но я думаю, это связано с точностью аппроксимации. Там мы использовали точность аппроксимации 16 мм. Для более высокой точности и модель будет сложнее, и точность, и скорость вычисления будет намного меньше. Если касательно железа, да, на котором мы использовали, то это был 8-ядерный процессор, то есть 16 потоков. Есть, конечно, проблемы с критическими секциями, и то есть когда работа потоков замедливается. Вот. Но я думаю, мы этот вопрос решим.
Угу. И это вы делаете эту работу в рамках БГТУ, да?
Я думаю, да. Ну, как по проектам у нас. Я не знаю, как объяснить.
Так, и вот эту систему потом вы планируете где-то использовать вот в виде...
Да, мой коллега, он чуть дольше занимается в этой сфере, у него очень много наработок на различные роботы различных структур. И вот изначально вот он использовал первоначальный метод, где очень много объектов, и когда, допустим, эту модель нужно как-то продемонстрировать или какую-то провести работу с ним, провести анализ, то это очень затратно. А вот модели, которые проведена триангуляция, либо уменьшение такого прямоугольника, вот это первый подход, то есть достаточно меньше ресурсов затрачивается и работать проще. Последующая обработка данных.
А если все-таки говорить о прикладном применении, да, вот в каких робототехнических системах это, на ваш взгляд, будет востребовано? Или это универсальный какой-то метод?
Нет, опять же, я вот могу вернуться назад, да, мой коллега Дмитрий, это касательно уже его работы, что он предложил новый метод использования данных, то есть обычно используют точки, да, там какую-то область показывают точечно, в которой очень сложно, например, найти конкретные координаты, да, вот принадлежит ли точка области, и перебор каждой точки достаточно затруднительный. И Дмитрий вот предложил новый метод, что объединение в параллелепипеды вытянутые, и эти параллелепипеды, они упорядочены, то есть имеет примерно такую структуру. То есть если область разбить на слои, то есть, допустим, в этой участвует только X и Y, то, зная конкретный Z, да, мы можем найти этот слой, и по слою, допустим, нам нужно определить X, мы идем, ищем X, вот у нас находим какой-то конкретный нам нужный вытянутый параллелепипед. И дальше мы проверяем, что находится ли наша искомая точка вот в этом диапазоне. А почему диапазоне? Потому что параллелепипед имеет начало и конец. То есть там нет прям каждой точки описаны. Начало, конец и где по X находится.
Ну, то есть, я правильно понял, это вот рассчитано на какую-то адаптивность, да, вот в робототехнических системах? С помощью вашей модели робот становится более адаптивным.
Скорее, это не робот становится адаптивным, скорее рабочую область проще работать с ней. И, то есть он не совсем этот метод унифицированный. То есть, если его сделать унифицированным, то есть это нужно будет еще какой-то модуль дописать, чтобы преобразование какой-то любой рабочей области преобразовывалась в конкретную структуру, чтобы уже алгоритм мог с ней работать. Но вот если вот именно в таком представлении данных, с которым вот мой коллега Дмитрий работает, и все наши роботы и манипуляторы, они описываются вот такой вот системой, то оно будет работать для любого робота.
Хорошо, я вас понял. Коллеги, у вас вопросы есть? Может быть, у Рустама вот годится ли эта система, например, для управления поездами, да? Вот насколько это возможно?
Ну, как бы сказать, само управление поездами, это...
Ну, можно ли ее как-то внедрить, да? Вот понятно, что это не панацея, но вот в какой-то модуль, например.
Не, ну, насчет управления поездов, то есть, когда уже понятно, что где находится, в принципе, не очень сложные алгоритмы нужны. А так, развлечение, как бы сказать, машинальное обучение насчет визуальных этих восприятий, это, конечно же, здесь совсем другое дело.
Но мы не стоим на месте, мы стараемся развиваться, поэтому я думаю, в дальнейшем мы улучшим наши алгоритмы.
Не, если возможно получить что-то такое транспарентное, то есть какую-то прозрачную систему, которую можно понять, то есть где можно понять связь между картинкой и результатом, то есть это было бы хорошо, да. Да.
Хорошо, тогда передадим слово, да, следующему докладчику.
Спасибо.
Да, сейчас мы посмотрим. Алия Шарипова, по-моему, у нас, да, она... Алия, вы здесь?
Да, я здесь. Добрый вечер.
Добрый вечер. Так, пожалуйста.
Я хотела бы уточнить только, я так понимаю, можно на русском, да, но у меня презентация на английском, поэтому позвольте.
Нет, наоборот, если вы на английском и вам комфортно, то вы можете на английском, это приветствуется. Тем более вот у нас появился коллега из США, да?
Хорошо. Okay. So our research now is in initial stage. So we propose like a concept of smart robot advisor for informed investing decisions. In recent decades, the development of technical opportunities for investment in various financial instruments of exchange markets and the interaction of all market participants have led to great interconnection of both developed and emerging markets. The ability to invest in various financial instruments, access to online platforms, and mobile application implementation has increased the accessibility of individual investors. Here on slide, you can see that nowadays a growing number of individuals have become interested in increasing their investment beyond part against conventional savings. This has been facilitated by attractive investment conditions and simplified entry to the stock market. According to the Moscow Exchange data, so you can see that in this year, the number of individual investors and this number is growing exponentially. According to Russian National Association of Securities Market Participants, there is the data that in this year, the current year, the unique number of individual investment accounts exceed more than 4 million. The appearance of individual investment accounts was supposed to attract private investors to the financial market due to the returns being higher than those of bank deposits. However, the problem of choosing the investment method, platform, and type of instrument and the portfolio strategy itself remains of the main ones for the investor. At present, a bank deposit is one of the most obvious and easiest tools for individual savings. Currently, investors with a small account of capital are interested in the stock market as an alternative to bank deposit. It can be concluded that investors would prefer to diversify their financial resources, both in bank deposits and in the new opportunities provided by investment products. The methods of individual saving and investing require making an investment decision in terms of risk tolerance. Investors with low risk tolerance prefer instruments with guaranteed returns on investments such as bank deposits, bonds of federal loan bonds. These tools guarantee the return in the end of investment. So investors with higher risk give preference to financial market instruments such as forex market, like currency pairs, stocks, indices. Individual investment assumes that the selection of financial instruments, invest horizon, and the necessity of return on investment analysis of an investment strategy in various market conditions. However, the investor is not offered methods for evaluating the return on investment without contacting an asset management company or determine investment parameters using a robo-advisor. In most cases, deposit assessment in financial market growth period is shown as an expected value of return on an investment. And the investor can make a decision only based on the expected return level, and its estimation does not take into account the financial instrument price deviation. This means that risk assessment is not performed. Many individuals prefer investing in mutual funds in the hope of a return on investment in the long time period, because the portfolio value is expected to increase over time. However, today it is necessary to focus on the advantages of index investing. The technical tools of investment development, the availability of technical analysis tools, and the access of individuals to the stock exchange led to exchange-traded funds as a further development of the mutual fund idea. The placement of this instrument for trading on the exchange provided the investor with the opportunity to use all the advantages of index investment, which with much lower cost compared to mutual funds. Well-known asset management companies such as Vanguard and BlackRock offer ETFs along with traditional mutual funds. The difference between ETFs and mutual funds that ETFs, so they do not try to get ahead of stock indices, but they assumes to replicate the dynamics of any asset or index as closely as possible. ETFs is a liquid instrument, enables investors to implement various strategies themselves instead of turning to a portfolio management or asset management company. Accordingly, this tool is interesting when an investor wants to form a transparent portfolio of investment in certain foreign assets and to reduce the role of portfolio manager and paying less for the management of the investment. Here you can see also the data from Moscow Exchange. analytics about the numbers, like the share in total individual investment accounts turnover by types of financial instruments. Most of used instruments are securities, and we can see that the share of ETFs in this graphic is increasing. So nowadays it can be concluded that ETFs become more and more popular instruments for individual investment. So here I provide you a screenshot of mutual funds. So what we should determine when we try to buy some funds. So we just put the expected return, our initial sum, investment period, and then based on historical data, we get some value of expected return on investment. So to provide informative data on the investment results, a portfolio manager, the most attractive periods of an uptrend and sufficiently long periods, for example, 3 to 5 years, are selected. In this way, the salesperson can show the expected return on investment based on price values on specific dates. For example, the close prices of financial instruments. However, when considering data for a long-term period, the price movement of a financial instrument might experience both rising and falling trends. There might also be some periods of sideways trends, like no trend, when the price resides in a certain corridor. In such a way, the actual deposit value may differ substantially from the expected or promoted return on investment, being utilized by the mutual funds and asset management companies to attract new clients. However, the results demonstrated to the client depend on the exact data of the market exits and entry points. The uncertainty and results and associated risk with this uncertainty of deposit loss are typically left behind during the considered period. These are not taken into account in the evaluation of the mutual fund, asset management company, or robo-advice performance. Here, accordingly to the investment theory, risk is an uncertain thing of the investment result, and it's characterized by the random deviation of the asset price around the average value. Without assessing the deviation of the asset price from the average value in the period under review, and thereby defining the deviation level of the investment return depending on the point of entry into the market, it's impossible to correctly assess the possible profitability of the investment strategy and possibly a possible loss of the deposit. The analysis of the strategy of the return of the investment should be conducted not only in terms of the return to risk ratio. The evaluation of proposed strategies done by a financial consultant or robotic advisor or other existing means of individual investors should be conducted in another way. The evaluation should account for more data that's narrowly than selected discrete values of the profitability over a certain period. So here we, on this slide, we illustrate the proposed concept of the evaluation, the price deviation effect on return on investment over the same period. Here you can see line 1, it is the expected return on investment based on the value of the adaptive moving average indicator, AMA. This indicator of technical analysis, we can see what expected value of the priced asset will be in the end of investment period. Line 2 shows the return on investment for the pessimistic scenario, and line 3 represents the optimistic view. A similar interval approach has been successfully utilized in a completely different application domain, namely in the project evaluation and research technique, where the length of the project is assessed. So, using this concept as a base for investment strategy assessment, we use the PINEX China ETF financial instrument, price data from Moscow Exchange. And here you can see return on investment for uptrend period for 6 months. So you can see how the price deviation around average value is different. So next slide, it's return on investment for downtrend period. And if there is no trend, so it's a sideways period, some corridor price also presented. Using this data of price of assets, we define the return on investment for all these scenarios. So first, the expected values are given based on the average values of the asset price, and also return on investment are determined for optimistic and pessimistic scenarios. Here you can see 2 periods for the same financial instruments, PINEX ETF. And as can be seen from the results presented in these tables, values of return on investment of considered scenarios differ significantly. The largest return on investment variation is observed for 6 months of investing. It can be concluded that this period is insufficient to obtain the expected return. The investment result depends on market entry and exit point. Thus, it's essential to include potential values of the deposits at the end of the investment period, adjusted to price deviation in risk analysis. So it's impossible to present a realistic overview of investment strategy efficiency analysis to investor without demonstrating the potential risk. These risks can be visualized as the variance of the asset price, thus assisting in the choice of the type of investment strategy according to the investor's profile and his risk tolerance. In most cases, asset management companies demonstrate the recent periods of growth of the periods of recovery right after the crisis, when the uptrend can be easily observed. With trading opportunities, investment is focused on long-term strategies with the goal of increasing the value of portfolio assets. Therefore, asset management companies should inform the client about potential drawdowns of deposits that are inevitable in periods of downtrend and sideways periods. Today, while the profit is presented in the form of an attractive graph, the risk warning is given to the client as a document to sign. which is very poor form of an attractive to inform clients about the investor about the real risks of deposit loss. Additionally, the investment period may be chosen not long enough to realize the potential growth of the fund. So the investor has online access to stock quotes, charts, investment company fees, and analytics, a different pool of strategies and tools for developing an investment robot, as well as different expert opinions. However, decision-making on the choice of financial consultant, trading robot, asset management company remains at the same level. The problem of the investment efficiency analysis and the valid choice of the investment strategy or portfolio manager appears complicated. Some instruments attract investors by a high return on investment, while the actual information of potential risks is not always demonstrated to an investor in the appropriate way. Many investors starting their activities may lose their deposits choosing randomly the asset management company or robo-advisor. The problem of management company choice is a challenge for the beginning investor. At the moment, the choice of a management company is based on the demonstration of the investment strategy profitability, which does not provide an objective estimation of portfolio management activities in various market conditions. It's essential to estimate strategy investment results based on the demonstration of the return in the context of price variation. So here you, on the slide, you can see parameters of robo-advisors, which are common for all robo-advisors that we analyze, and include such parameters like investor age, investment horizon, risk tolerance, and expected return on investment. And some researchers, they obtained result that robo-advisors are not sensitive to parameters such as age or experience of investment, which ultimately affected the financial result. Based on the investor's preferences, it's assumed that the robo-advisor will select financial instruments by type of risk investor, conservative or aggressive investment. However, the robo-advisors chooses from the available portfolio. Individuals can give the same questions to standard answers to standard questions, even if they look for portfolio construction is completely different. Increasing interest in individual investment tools might put a strain on choosing a limited set of portfolios. This might result in the necessity of using an automated investment decision-making tool. So here we, on this slide, we present a concept of smart robo-advisor for informed investment decision. So robo-advisor provides the investor with the demonstration of return on investment assessment and potential deposit drawdown according to potential price volatility deviation. Artificial intelligence is embedded in smart robo-advisor and provides the investor with an instrument for achieving the investment strategy with technical indicator parameters implemented in the strategy decision support system. Financial instrument quotes, as well as risk tolerance and expected return on investment values determined by investor, are fed to the network input. The smart robo-advisor forms the investment decision concerning investor requirements based on neural network. So this work presents an approach to the individual investment decision-making process in the context of price deviation assessment. The proposed method of return on investment estimation enables to investors to make decisions more informed among the diversity of information and investment tools. It's essential to provide the investor with an informed decision-making tool based on the return to risk objective analysis. So we propose using a graphical representation of the expected return on investment in the context of financial instrument price deviation from the average value. Despite the variety of investment tools and analytics, asset management companies are not able to provide investors with a real individual approach or in particular offer typical portfolio solutions. Standard return on investment assessment is not enough for making a valid investment choice of investment strategy or portfolio manager. And this, we propose to implement an automatic smart robot advisor as a tool for informed individual decisions. This might increase the number of satisfied clients and the awareness of individual investment tools. Thank you for your attention. So, do you have some questions?
So, friends, do you have questions?
Okay, I'm not expert in financial machine learning, as I understood. I just have a very rough understanding. There's a saying that predicting is difficult, especially if it's future. How is the validation done of the model? How do you know that it's not broken just one day after?
Thank you for your question. So here, as I mentioned above, it's work in progress. So we just proposed a concept of price analyzing the expected return on investment. As you tell, that prediction is really a challenge, and nobody knows what price will be in future of security or other financial instruments. So we just tried to propose this concept like the price deviation. So to demonstrate potential client that the return may be on this level, or if it will be downtrend, you can even lose your money, your investment, or it can be an optimistic scenario. So we propose to include this concept to this robot advisor, just to make more involved the investor in his investment decisions. Because nowadays, all well-known advisors, like VTB, Sberbank, or some other companies that provide this robo-advisor. So you just put your risk tolerance, age, and expected return on investment, and the period of investment. So it's really not enough to make informed investment decisions. And we do not make validation of the system because we it's our future work that we will develop this smart robot advisor for this concept.
Okay, thank you very much. As I see there are no other questions, I will give it to Nikolai Katargin.
I'm sorry, we have a question.
Okay.
I have okay.
One of the members that's here.
Have you considered any crypto investments in your work?
Sorry, could you repeat the question?
Have you considered any crypto investments in your work?
No, we don't consider it because it's really new financial instrument, and it has some characteristics that I think, like today, a bank deposit is a most popular instrument. Yes, a lot of many investors they don't trust such instruments, and we can see like in 3.5 last year, the number of investors become to increase. So I guess like such instruments like crypto currencies, it's not really a good idea for attract new investors and make informed and valid investment by individual investors.
Okay, thank you.
Все, видно, да? Так, ну ладно, по-русски тогда извиняюсь. No, maybe in English immediately. The artificial intellect include my report to your section because it deals with not so robot mechanisms. Mechanic robots look like humans or look like animals, but I want to redetermine the word of robot because I try to use it for social systems. First of all, for social systems, economic systems, they may be described only in multidimensional space. And the simplest example of enterprise in multidimensional space here is it's building tools and etc. And it is multidimensional space. And we can свернуть to image it in the coordinates K and L is usually it's simplest model of Cobb and Douglas. And we can calculate, evaluate result of our investments. No, it may be NPV, it may be income. No, maybe I'll use the term and power of the system to exclude. No, чтобы не заморачиваться. And I propose to use for description of social and economic system not K and L, but mass and information. Such variables as mass and information. And according to the theoretical physics, use as coordinates speeds изменения, скорости изменений, speed of production of speed of production and speed of information processing. These indicators may be evaluated using unified units money. And social and economic systems may be described in such such coordinates M, I, and the speeds of the changing. In a social system, the cost of any of goods mainly is approximately 90%. It is information, and approximately 80%, maybe more now in developed countries did not work in production by hands, by tools, but in processing of information. And face volume, here, we can evaluate approximately to 80%. It is the main money. And it's a political model, as I know, that the states who sell natural resources or maybe metals, they are poor countries. But here is countries who use knowledge is in industry, and here is most prominent maybe countries who can produce symbols, образы, social and economical models, and it's most valuable production, systems, social and economical systems. It is open systems, and the flows of energy and material pass through the systems, and the flow of information. And due to these flows, maybe образовываться may appear objects in atmosphere of the Earth. Such objects, it is typhoons, tornadoes, but here in information system, in information sector, may appear objects with high, very big, consist of money, information and money. And so the economy struggle and money are concentrated in such objects, concentration in this sector and in these objects. And this simplest analog of these objects, it is the button at the memory of computer. It is computer code, and we can see the image supplied by this computer code, and this object, or its usual this object, the computer memory in the information space, can react to the events such as click and produce signals for managing, for handling of mechanisms. But in social systems, there are complex objects, such as financial models, chimeras, hypes, especially interested hype, of course, and the robot, pure robot, without peoples, without humans as part of executive mechanism. It is what a missile attack recognition system and for strike control. It is a robot, typical. And these such robots, such systems consists of program code and executive mechanisms. It is robot, but is not a robot, look like a human or animal, but a robot in a social system, a gene system. Sometimes really such as missile attack recognition system. It is a robot, and it may be without people already. Now such systems include people, include humans. But if Americans would install rockets in Europe, especially in Ukraine, they want, and Russia would install their rockets along the border. There would be only robot would decide about attack, and our life would depend on only these robots. But such robots at finance systems, IT, media, justice, it is robot tool, robots tool, because they consist of some codes in memory of computers, or in paper maybe, but now it is not in paper, texts in computer too, such as legislation. And so the structure of global social economic system turned upside down, and usual structure is people need to eat, to build, and they need in economy a system for supply people these goods, and economy need in businessmen who manage it, and government. But business need in finances, and the banks concentrate money, and they now are under business and under humans. And the last years, it is added by IT, mass media, and justice. And the main money, it is in this block, not here, not usual business, not in economy, but in this block. We can't see this object, this informational object, and with executive tools. But it exists. It exists. And it managed not business, no usual business, real business, material business, but countries, governments, and people, and humans, and humans. And it is a really struggle. It is a real war between such robots. It is robots and civilization of humans. As an example, you know that the main part of money in the United States, it is namely in banks, IT, mass media, justice, and they depressed their industry. Donald Trump tried to change this situation, and real material businessmen and people voted Donald Trump. But you can see how this bloc win Donald Trump. It was a very big attack at Donald Trump. How it's related to Russia? Russia and not only Russia. I can say that you know that it was Cold War between Soviet Union and United States and the capitalist countries. It was not only military struggle, but struggle in information space for some ideas. And due to traitors in the government of Soviet Union, the Soviet Union crashed down, and it was the finish the World War III. It was without armament, without battles, but as you know, the result of the crash of Soviet Union for people in the former Soviet Union is damage was more than due to the Nazi invasion. No, it's in Russian. Some cite from Kovalchuk, director of Kurchatov Institute, that we are living now in the condition of war, and their attack, not military attack, no, but attack to education, culture, economics, science, etc. And colonization is not by military, but technology. As example, Kovalchuk say, so-called World Health Organization, but maybe it's good. But now this organization try to manage all over the world. It wants to be under government. And for example, former president of Russia, Medvedev, told about it. And about this is citing of Andrei Ilnitsky, that the instrument of the war and peace are approximately the same. And we can't and we can't understand it is war, or maybe it is not a war. And the frontier of the war, it is not through ground in fields somewhere, in fields and in forests, but through brains of people. And it's interesting. It is not war between states, between countries, but between systems, between robots, and civilization of robots and civilization of humans. But humans want to live. The purpose of robots, it is only profits. Because any company, any bank organized namely for profit. It's good, principally it is good, but if this organization became very big in the scale of world, and it tried to extract a profit, but it became under the humanity, and it is not good. And such countries and some people try to struggle with it. And here I tried to strike the frontier between robots and humans. Its purposes of robots, it's only profit, but humans want to live. Objects, corporation, banks, and usual states, and instruments of robots. It is many genders, such as LGBT, and as an instrument, it is education. And if you see about the countries, states, no, mainly robots, it's USA, and anti-robots, it's Russia, China, Belarus. But you can see that Donald Trump and half of United States, they are anti-robots. They were formed by Hollywood, and they want to live, to have usual families, children, but the Democrats, they try, no, you know about struggle of governmental and especially social organization in United States, such as LGBT, it struggle with usual humans. And in Russia, in the side of robots, such big robot companies, such as Grev, Kudrin, Fursenko, and I can't say about leaders in Russia. Vladimir Putin tell very good about rights of humans, about saving of population, and development of Russian economy. But Grev, Kudrin, Fursenko, they are friends. Вопросительный знак поставил. Вот. Ну, let's say about liberal model. Да. And such persons, люди, such persons, they are not so Russians leaders, but Russian managers, super managers, but they are members of international organizations, such International Monetary Fund. The frontier is not through fields and forests, but through brains, through between us. And about such, I can say that our Ministry of Education, two Ministry of Education and one Ministry of Science, they are robots too. As you know, there are no specialists in science and education in these ministries. They are managed mainly from United States. And for example, as example, the Bologna system была введена for the request on the International Monetary Fund. It is Russian schools, education in schools using George Soros system. And the demand of publication of Russian teachers, Russian professors, only in foreign journals. It is destruction of foreign. In results of this system, it's you may ask, maybe not a high economical school, maybe, but in financial academy, the National University, I ask sometimes students, they don't know about where the Volga flows с кем Суворов воевал, что Петр Первый сделал, они не знают. Вот такие вот результаты именно борьбы таких систем с реальными людьми. And here is result of the education, result of the struggle of organizations, robots, through real robots, through social nets, через смартфоны. Вот, I can see this picture in my lectures sometimes. Not everybody, of course. Конечно, не такая карикатура, но тем не менее вот это вот весьма популярная вещь. It's practically that's all. Niels Bohr said about some physical theory. This physical theory is not too mad, недостаточно сумасшедшая to be true, недостаточно сумасшедшая, чтобы быть истинной. Вот. And I wanted to say about specific unusual point of view for investigation of social and economic systems, and maybe it would be useful for somebody. Thank you. Thank you.
Okay, thank you. I have just immediately a question. You have one slide.
Ой, можно пару слов?
Да, у меня как раз появился вопрос. У вас там был один слайд. Вы разделили общество на блоки. Между прочим, насчет этой идеи роботов или даже, можно сказать, алгоритмов. Я написал статью, я сейчас ее бросил в этот, в чат, но я все совсем другими словами описал.
Ну вот интересно было бы это самое. Вот, я могу в чате свою... Так, можно писать, да?
Не, ну, я описал это более с позитивной стороны, что если алгоритмы будут управлять обществом, что может все-таки быть в лучшую сторону? Да.
Алгоритмы...
То есть, конечно, будущее можно смотреть утопически и дистопически, да, то есть можно на одни и те же вещи можно смотреть хорошо и плохо, да, то есть я подумал, если мы заменим управление обществом алгоритмами, что при этом может измениться? Что можно заменить? Что невозможно заменить? Да.
Так, это я свой этот самый... Сбросьте, пожалуйста, мне, я тогда...
Я вот в чате, вот посмотрите, вон там в чате я свою статью кинул насчет этого, что в принципе такое более с теорией игр, да? Я теоретик игр и как бы сказать, и делал эксперименты с людьми.
Это. Ну, она есть, но я потом, как не знаю, доберусь до нее. Ну, вот ННН ККК, если сбросить, то будет или ссылку, или что-то, то с удовольствием. И я могу свое сбросить многое. Так, хорошо или плохо, если роботы будут нами управлять, да?
Да.
Понимаете, какая тут вот именно задача-то, какая цель стоит? Да, конечно, вот автоматизированные системы управления экономикой, их давно пытаются сделать, не знаю, насколько хорошо это получается. Ну, в Советском Союзе пытались сделать. Но дело-то вот в чем. Ну, и по-русски скажу буквально то, что я говорю, что любая компания в бизнесе, компания, банк, она стремится к профиту в конечном итоге. Других целей она, по идее, не должна ставить. И действует в рамках, которые ей ставит государство, народ, который ее ограничивает. Ну, чтобы там природу не загаживали, чтобы там рабочих кнутами не били. Вот, да, вот в рамках ограничений должна максимизировать доход. Вот. Но если эта компания, она встает над правительством и над людьми, то она превращается в робота, вообще-то говоря. Она вот обеспечивает этот доход, независимо уже ни от чего. И люди ей служат. Я вот статью забросил, там есть, что люди могут понимать, что это плохо, но они ей служат, а деваться некуда. Кушать хочется.
Вот. Ну хорошо, это понятно. Это если как бы, а в чем состоит этот профит? Это что, раздувание техносферы, в принципе? Ну, в принципе, профит-то он не может быть полностью воздушный. Да?
Ну, в общем-то, да.
То есть все больше и больше всего этого материального, да?
Ну, реально вот получается, что это профит, это деньги, и деньги для, что называется, ограниченного количества людей. А остальные превращаются в биороботов, и вся система работает на то, чтобы заставить людей... Ну, сейчас вот действительно кризис, который происходит, он сводится во многом к чему. И, кстати, и Путин об этом толдычит. Правда, почему? Что вся система ориентирована на этот NPV, что значит много добыть, много наделать, много продать и много на помойку вывести. С тем, чтобы вот заработать деньги.
Да. Подождите. Но это же невозможно. На ограниченном количестве ресурсов невозможно.
Да, ресурсы уже заканчиваются. Их ресурсов не хватает, а людей много. И поэтому вот Путин, кстати, заговорил, что надо не NPV, он как-то говорит по-другому, не NPV, а в общем-то качество жизни людей. Вот. А у меня есть работа, я утверждаю, даже до лабораторки доведена, прям со студентами гоняю, качество не жизни людей, а самих людей. И, кстати, китайцы это реализовали. в Китае, у них главное именно вот даже не железо наделать, как вот железо делается для того, вот скоростные дороги, чтобы сделать хороших специалистов, людей. У них главное, и они наделали людей на самом деле уже хороших патриотов, специалистов. Вот. И сейчас они достигли уже, так сказать, среднеобеспеченного общества и великой державы. Вот они это сделали.
Хорошо, вы мне, как его, вы мой линк увидели, и вы можете как-то, может быть, мне там в чате скопируйте линк, и мне тоже как-нибудь пришлите. Вы меня в интернете сможете найти, имейл-адрес там тоже есть.
Есть, да? Ну, мое простенькое совсем, это самое, НННКК, Яндекс.ру.
Хорошо,
вот,
хорошо.
Чего-нибудь.
Так, я переключусь сейчас на английский.
Нет, НННКК, Яндекс.ру. Я пришлю, что интересно там. У меня, говорю,
хорошо, я увидел ваше имейл. Хорошо, все. Я переключаюсь на английский. So, thank you very much.